with that. Okay, so. Okay, we can turn up the lights a little bit. That's better? Yeah. I think intermediate. Do you want them all the way on? Okay. Okay, so a couple of housekeeping things. First off, there's a quiz that begins right in class today, but you have until Wednesday at 10 a.m. to complete that. So you have quite a bit of time. This is like the first real quiz. Also, I'm going to reopen the first quiz. I know some people still missed it. I'm going to open it from right after class until 5 p.m. today. And you can take it at this point if you didn't take it before for a 20% reduction if you didn't get it in before. I was looking at some of them. Yeah.
Can we retain it if we screwed up the name part?
The what part? Or the name part? If you want to retake it, I don't think you can. No, your probation's closed on that. You're done. You were cut off. And in fact, when I grade it, I will probably try to unenroll you from the class as well. Okay. Okay, this thing like sticks open. And I keep bumping into it. And then here, the funny thing is I close that one, that other one pops open. That's grand. What's that? No, I can't. Okay, let's keep talking about enzymes here. And we're going to start talking about enzyme inhibitors and how enzymes are regulated. And one of the first ways that we're going to talk about that is by regulate or by inhibition. Now, there are two broad categories of enzyme inhibition, and the first are irreversible inhibitors. And irreversible inhibitors bind covalently to enzymes. So they are binding very tightly to these enzymes, and this binding is going to be irreversible or permanent. So an irreversible inhibitor, that enzyme is done for. The only thing that you can do with that enzyme is now degrade it and recycle it, and it's toast. Generally, biological systems don't make. Let me back up. If you're trying to regulate your own enzymes, sometimes you will make inhibitors to regulate your own enzymes. You tend not to do irreversible inhibition on those. It's kind of expensive to have to recycle those enzymes again. So we tend to use the other kind. Now that being said, there's actually quite a few toxins, like venoms, that are irreversible inhibitors. There are some toxins, for instance, like tetrodotoxin, well, it's not quite an enzyme that's inhibiting. I won't use that example. A lot of venoms and toxins are irreversible inhibitors, though, and will inhibit. Oh, here's a really good one. No, those are still channels. Okay, never mind. I have a lot of good examples, but they're all like in my head, but they're all so like ion channels. And we'll come back to those when we talk about membranes. So forget I said anything. I'll keep embarrassing myself. Okay, in the meantime, let's go talk about the other kind, which are reversible inhibitors. And of the reversible inhibitors, there's two kinds I'm going to talk about. Actually, there are more kinds than just the two, but I'm going to talk about these two kinds. And the first kind I'm going to talk about are competitive inhibitors, or competitive inhibition. In competitive inhibition, your inhibitor resembles the normal substrate of that enzyme, and it competes for the active site. So both the inhibitor and the substrate both want to bind to the active site, and therefore, when the inhibitor binds to it, your substrate can't, and that prevents the enzyme from actually catalyzing the reaction on your substrate. And this keeps it from working as well. When these bind, they bind non-covalently, like anything binding to the active site is not covalent when it binds. And because it's competitive, if you raise the concentration of your substrate, you can overcome competitive inhibition. The way this happens is essentially you can think of an enzyme, again, going through like the example of me looking for toys or picking up toys. Imagine I'm blindfolded and there's both toys on the ground and my daughter's I'm picking up, and there's something else that I don't want to pick up. Let's imagine it's grenades. Okay, good, grenades. But that's like if they go off, that's like permanent inhibition. That's irreversible. If a grenade goes off my hand, that's pretty irreversible. Snakes. What's that? Sniper. Oh, diapers. Diapers. I pick it up, it's a sniper, and I diapers. Well, the problem is I want to get rid of the diapers too. What's something I want to keep on the floor? Snakes, let's say snakes. Okay, for whatever reason, I can pick it up as a snake. It's not poisonous. Okay, whatever. Okay, let's say this. Imagine in my house, I have this really big snake room that snakes just live peacefully, okay? And my 2-year-old daughter also plays in this room. And she'll sometimes leave her toys in it, right? Okay. Bear with me for a second. This will go somewhere. And I am blindfolded for whatever reason. I'm blindfolded and I'm trying to pick up all her toys in the snake room. So I go on blindfold, I pick up a thing. If I pick up a toy, I'm like, okay, let's put that away. I'm reacting it, right? And then I pick up a snake. I'm like, oh, this is a snake. It needs to stay in the snake room, so I put it back in. Does this make sense so far? Okay. If there's kind of comparable concentrations of both, the presence of the snakes will slow me down, as opposed to just having toys in there. Does that make sense? Because every once in a while I'll pick up a snake and be like, oh, it's a snake. I'm blindfolded, I can feel it's a snake. It needs to stay in the snake room. Okay. Thank you for helping me out with this metaphor, this extended, crazy metaphor. Now here's the funny thing. Let me back up for a second. This isn't as crazy as you think. When I was growing up, my dad raised all sorts of crazy animals. Like this is like the household I grew up in. He would buy all sorts of things, and he would breed them and sell them back to dealers and pet stores and stuff like this. We took our two-car garage and was converted into an animal room, okay? And in there were geckos and tortoises and walking insects and beetles and tons of tarantulas and iguanas, and I already mentioned the geckos, beetles.
Childhood dream.
What's that?
That's a childhood.
Yeah, it was great. I mean, you had to be careful. There's some things that were poisonous. But you know, but here's the thing: is like this might sound crazy. Kind of not crazy. Anyhow, so I'm in my snake room. 2-year-old daughter's messed it up. But here's the thing: that's competitive inhibition. Now, if it was a grenade instead of a snake, that'd be permanent inhibition, like irreversible inhibition. My hand is gone. I have to be recycled. Weird now, like a dystopian sci-fi dark film there. But in the happy film, I'm picking up snakes. They're not poisonous. I put them down. If I get enough toys, if there are so many toys that there's like 1,000,000-to-1 ratio of toys to snakes. Imagine there's like knee-high toys, and there's one snake in the room. Don't have nightmares. If there's that kind of ratio, is the snake going to really slow me down? Provided I'm not scared of it. Yeah, no. Like, it's going to be very rare that I ever pick up that 1 or 2 snakes, and I'm always going to be picking up toys. And so that's what's happening here. If you raise the substrate concentration, it overcomes that inhibition. As long as you have a lot more substrate, like a lot more substrate than you have an inhibitor, you will overcome that. Now I'll have to ask you a question on the test about snakes and toys and yeah. Okay. So, especially after I spent that much time on it, I really have to ask you a question now about that. So, think about this. Vmax. What does Vmax represent? The maximum rate enzyme can go when you hypothetically the substrate is at infinite concentration. Would Vmax be affected by competitive inhibition? Nope. Vmax not affected. Okay, let's think about Km. What does Km what does that map to? What does that represent?
It's the substrate concentration at which V will be matched.
It is. Do you think that Km would be affected by what's that? By competitive inhibition, my bad. Or by snakes. That's the other way I could say that. Do snakes affect Km?
Probably.
Well, probably. I mean, if it's dependent on substrate concentration, then wouldn't it affect?
Yeah. So let me pull one thing I said. When I was talking about Km is a measure of the affinity of the enzyme for the substrate. So it's essentially how quickly does the enzyme latch onto the substrate. If you latch on more quickly, you have a lower Km. If you latch on less quickly, you have a higher Km. Now think about it. A competitive substrate, is it going to change how quickly or how readily an enzyme latches onto the substrate? Yeah, because half the time it's going to be latching on to, if you have a roughly equal portion, half the time it's going to be latching on to something other than the substrate. And so it's going to affect that, or half the time you're going to be picking up a snake. And so it takes me longer to pick up the toys. Now, if there's infinite concentration of toys, then it's the same rate. But in the middle ground, it does have an effect because it takes me longer to pick up a toy. So what this means is that Vmax is unaffected, but Km goes up under competitive inhibition. And Km goes up because you have this apparent lower affinity between the enzyme and the substrate. It's not actually a lower affinity, it's just simply that you're latching onto the wrong things half the time. Or whatever percentage of the time that's the ratio between your substrate and your inhibitor. Okay, so just to kind of give you an example here, this is how this goes. Go along the top, you have a normal reaction where the substrate binds to the enzyme. You have the enzyme substrate complex, and then it releases the products. Below, you have inhibition where something else binds to the active site, and that prevents the substrate binding to the active site. Yes?
Will an enzyme always have one activation site, or will it have multiple activation sites?
So it depends. Generally, you have one active site per polypeptide. However, for one particular substrate, generally, that's not always the case, but generally. However, many enzymes have multiple subunits, and sometimes each of those subunits have an active site for a substrate.
So how do you account, if there's multiple different things in the substrate and you don't want to pick it up, what would do you account for if you want all of those things for it to pick up? Do you choose an enzyme that has multiple sites?
I'm not quite sure what you're asking. So you're imagining there's an enzyme now that has multiple sites.
Right.
Generally, they act somewhat independently.
Okay.
So somewhat independently. So one combined while another was inhibited. Okay. So they kind of act as independent enzymes to some degree. Now that's not exactly true. Generally, there is some sort of cooperation between them, where it makes it easier to react more once you have some of them reacting. But for most purposes, we can ignore that for the moment. That kind of make sense?
That makes sense.
Okay. Let's think about your Lineweaver-Burke plot here. So here again, we have Lineweaver-Burke that we were talking about on Wednesday. And so this is 1 over substrate plot versus 1 over V. And how would this change if this is the normal uninhibited enzyme line? How would the line change for a competitively inhibited line. Or a competitively inhibited enzyme. What's that? Slope would increase? Who said that? Oh, good stuff. So yeah, the slope would increase. How would the intercepts change? What's that? Would it?
Which intercept?
Well, that exactly. What would happen to each intercept? So let's talk about the y-intercept first. How would the y-intercept be?
It would change.
Wouldn't change, yeah, because that is when the review mass. So that wouldn't change. What about your y or your x-intercept here?
It would change.
It would go closer to the what?
To zero.
To zero? Yeah. So it would then move over here. Very good. So yeah, that's exactly what you have. So the dash would be the competitive. The slope goes up. Slope increases because your rate is going down. You inhibit an enzyme, the rate goes down. So since this is 1 over the rate, this is a reciprocal of the rate, the slope goes up. Vmax unaffected, so that means that your x-intercept should remain the same. And your Km will actually go up, which means that since this is negative 1 over Km, this will actually go closer to 0. It also goes up, but closer to 0 is easier to think about, at least for me. Okay, let's talk about non-competitive inhibition. So non-competitive inhibition, this is when your inhibitor binds to a different location than the active site. And this causes some sort of conformational change in the enzyme that prevents it from completing catalysis. Now that being said, it does not interfere with the substrate binding. So let's think about this for a minute in my snake room analogy. I am blindfolded in the snake room, picking up the toys of my daughter, and I can either pick up a snake or a toy. Let's imagine there are no snakes, so we're going to get rid of the competitive inhibitor. So we took them out because, I don't know, insurance reasons. I can't actually keep snakes. I don't know. Is there a snake? So I gave them to a zoo. I don't know. But I have my bucket, I pick up a toy, put it in the bucket. Pick up a toy, put it in the bucket. Again, I'm blindfolded, and someone else wants to play a trick on me. So what they do is they have this bucket, they actually put a cover over the bucket. So the cover is over the bucket. It doesn't bind to my active site, like my hand is my active site. And I pick up a toy, all of a sudden I can't put it in the bucket because someone put a cover over it. How pathetic of that? What I'm seeing is this where I'm blindfolded picking up toys, and someone I extended metaphors a little bit too far, so forgive me. This is like non-competitive inhibition. It didn't bind to the active site. It didn't prevent me from actually picking up the toy. The enzyme binds to the substrate, but it did prevent me from sticking it in my bucket, like actually making the product, which is the bucketed toy. And so, for this reason, what happens if this were to happen? If you put a bucket on, like a cover over the bucket, would my Vmax change? Yeah. Like it doesn't matter how many toys you give me, I'm never going to be able to put them into the bucket if it's covered. Like it's going to slow me down like forever, in this case like to 0. Doesn't matter how many toys I have. So Vmax goes down, it decreases. Now think about this, what about Km? Would Km change?
The rate at which you're doing is trying to, wait,
No, you're right, you're on the right.
because the rate at which you're trying to grab your substrate is the same, it's just that it can't bind.
Yeah. I guess a better example would be It's not complete cover, but it has a little hole that I have to find that's a lot harder to find. How about that? And so the rate at which I pick up the toys is exactly the same. What slowed down is my absolute rate because it's hard to shove them in this little hole. And so I slow down, but that rate of slowing down doesn't have anything to do with how quickly I bind to my substrate. It has everything to do with how quickly I can then proceed with the rest of the reaction. Does that make sense so far? So Vmax decreases because that is going to slow me down. It does not matter how much substrate you give me, I will always be slower. But it does not affect how quickly I can pick up those toys. We're all good there. Yes?
It's like synonymous with
Yes. So this is, okay, so there's actually two subsets. There's like non-competitive and uncompetitive. They're both allosteric, yeah. And
so
I'm not going to,
type of allosteric.
what's that? They're both,
Type of
yeah,
allosteric.
yep. And both of those are a type of allosteric inhibition. But that being said, I'm not going to talk about uncompetitive. Yeah. Okay, so this is kind of the mechanism. This up there at the top, you have an inhibitor and a substrate. One of two things can happen. You can bind the inhibitor or you can bind the substrate. If you bind the substrate, everything goes swimmingly. Everything goes great. If you bind the inhibitor, two things can happen. You could also, that inhibitor could pop off and you could bind the substrate, or you could bind the substrate while the inhibitor is still on there. If the inhibitor is still on there and the substrate is on there, nothing happens. At some point, the inhibitor has to pop off, and then you can proceed through the rest of the reaction. And so you have an inhibitor that can be on or be off, but as long as it's on, it'll prevent the reaction from proceeding. And when it's off, everything goes swimming. So that's an example. That's not an exclusive example of the type of mechanism this could be, but that is a good illustration. So how would you expect this line revert line, to be changed from the uninhibited enzyme to the non-competitive change? Your wire set would be lower?
Yeah. Well, it would be, the wire would be higher because it's in the inverse.
Yes, in the inverse, exactly. And what would happen to the x-intercept? It's the same. Yep, and that's exactly what happens. $11:30. It's Friday. I still haven't got this schedule figured out. Just. I know. I'm not going to be sitting here at 11:30 and be like, "Oh, we're all done," and then you will not probably tell me about that at all, and just leave. I'll get back to my office. I will realize the folly of my ways. Cry. Like all the learning they missed out on because of my inability to remember crazy, archaic times. Okay, let's talk about metabolic control. How else do we control enzymes? I heard someone say something over here? Oh, nothing. Okay. I actually thought I heard someone say exactly what I was about to say, and I was like, ooh, you're reading my mind. Okay, one of the primary ways you can control an enzyme is by controlling the pH of the solution that it's in. So each enzyme is made to work within a certain range of pHs, and usually that's fairly narrow. If it gets outside of that range, its activity rate will drop off fairly sharply and go to 0 if it gets too far out. But that means then that you can adjust pH by just a small amount and regulate the rate of an enzyme, or actually turn one off completely. Give you an example of this. Here in the green is kind of hypothetically some enzyme rate, percent of its maximum rate at some narrow range. Looks like that one's kind of centered around 5.5 and 6. And if you get too far away from pH 6, it drops off, the rate drops off pretty quickly. Here's another one. You can kind of see there's not really any overlap there. So if you have pH of 2.5, the red one's going to be working pretty well, the green one not at all. If you have pH 6, the green one's going to be working pretty well, the other one not at all. Sometimes you have overlap. So again, a blue having a maximal rate at about 7.5. If you were at about 6.5, it looks like both of them would be working, but not very well. So, kind of giving you an example, we can move pHs around and regulate how an enzyme is working. The reciprocal is an enzyme is only going to work generally in a very narrow band of very specific pHs. This is one reason that if you change very strongly the pH of your blood or something else like that, you will start breaking. And one of the things that starts breaking first is all of your enzymes. So some of the ways that this can happen is, first off, you can have protons bind to enzymes at low pHs. And because enzymes are predominantly working through this delicate balanced interactions of the charges of the side chains and how those change when the substrate binds, if you're binding protons to that, that will change how those interactions happen. Reciprocally, at high pH, you can be releasing protons from the enzyme, and again, changing those interactions of charges along the side chains. And all of these changes will alter either the conformation and can also change the charges in the active site, both affecting how this enzyme is going to function. Sometimes I feel a little bit like I don't have like the skills of a real professor because I can't like just sit here and write like back in the day and just like I could never lecture that way. Maybe I should try. Okay. It takes forever. Pushing buttons are so much easier. I need to take a nap now. Okay, another way that you can regulate enzyme activity is through covalent modification. We usually bind things onto the enzyme. Here's the other problem. I write big, and so like the entire thing would have like 4 lines on it. I have to raise. Yeah, too slow. So some of the things is we can add or remove functional groups like a phosphate, like this. Stick one on, pull one off. This is actually a really common way in which you'll see covalent modification modifying the activity of an enzyme quite a bit. And again, we can do this through phosphorylation or dephosphorylation of the enzyme, which is going to be happening by kinases or phosphatases. Kinases phosphorylate things, or phosphatases chop off phosphates. Another way that we can regulate enzyme activity is through interactions between enzymes or interactions between the cell and the enzyme as well. So, for instance, in many places, especially where we have an entire pathway that's really important, enzymes can be arranged on the cytoskeleton or on organelles in such a way in which they are in close proximity to each other. And close proximity to each other in such a way that it's easy for them to pass the product of one enzyme becomes the substrate of the next enzyme. The product of that enzyme becomes the substrate of the next enzyme, and on down the way. By having this chain of events, these pathways in which we go product to substrate to product to substrate to product to substrate, and having all of these enzymes physically arranged near each other, we can somewhat artificially increase the rate at which they're going to be operating. Because again, remember that a lot of the time, one of the limiting factors in chemical reactions is going to be how often do these molecules actually collide with each other and interact with each other. If we can keep them close, essentially artificially in a very small, not artificially, it's natural, but I mean, keeping the concentration high in some local area, that will increase the reaction rate. And so we can control this by controlling physically in space where they are. So by doing this, we can form these multi-enzyme complexes also that have multiple enzymes kind of smashed onto each other, and then they pass products from one to become substrate of the other. So again, controlling the physical space in which they are in, and essentially has the effect of increasing the concentration of both enzyme and substrate in that small local area. And offers you a lot more control than you would have by a simple diffusion out into the cytosol. That's my diffusion test. My fingers are diffusing. You also have allosteric regulation. Again, a subset of this is the non-competitive inhibition that we talked about already. And this is possible because enzymes often have some binding site that's in addition to their active site that will bind other things. And that is known as the allosteric site. And binding to the allosteric site can either be inhibitors or activators. So let's look at one example of allosteric inhibition here that's different than the non-covalent. Here what we have is, okay, again, have your normal reaction on top. Down at the bottom here we have an inhibitor that binds to this. And because you cause a conformational change when that allosteric effector is bound to that enzyme, this one can actually changes the shape of the active site and prevents the enzyme from binding, or the substrate from binding to the enzyme. So that's another example of allosteric inhibition there. Okay, let's talk about another way in which we can control the rate of reactions, and this is by helping out our delta Gs. And we do that by coupling the reactions with ATP. So this is ATP. This is a nucleotide. We talked about this early on in the quarter, way back when, I think that was Wednesday of last week. And again, you have an adenine here, a ribose, and then 3 phosphates. ATP stands for adenine triphosphate, or adenosine triphosphate. Because once you get those things, that's the adenine, this whole thing is the adenosine. And we can couple the hydrolysis of one of these phosphate groups, so essentially cleaving that off, to another reaction. So chopping off ATP, a phosphate off of ATP to make an ADP plus pyrophosphate, you get a standard delta G, so a delta G naught of negative 7.3 kilocalories per mole. Remember, that's going to be modified though by your specific conditions like temperature, pH. And actually in physiological conditions, the actual delta G that you get from that reaction is about negative 11.3 kilocalories per mole. Which is a lot. So a kilocalorie is the same as a nutritional calorie with a big C. So it's like 11 calories of like food. I could actually calculate, maybe I'll do this for next year, is figure out if you had a hamburger just made of ATP, how many calories would that be? That'd be a lot. What's that? I wonder how that tastes. Probably not very good. Okay. So what we can do, though, is we can couple another reaction to this. So imagine we have a reaction of converting A to B. This was the grand thing that people wanted to do back in the day. Alchemy is turn A's into B's. If you could turn an A into a B, it would make a lot of money. And imagine this as a delta G of positive 3.0 kilocalories per mole, and that shouldn't normally happen spontaneously. Because we have a positive delta G. We actually have to have less entropy at the end of this reaction, which isn't going to happen. But what we can do is if we couple this into the hydrolysis of ATP, or ATP to ADP, that has negative 11.3. That actually is a bigger drop than the gain of the A to B conversion. Which means that if they're coupled together, this whole reaction then has a negative 8.3 kilocalories per mole. So that works. The whole system now does have an increase in entropy. And so, hey, we're okay. So ATP inside of you is constantly being consumed and produced. You're making ATP at very high rates, and then you're consuming it at a very high rate because this is essentially the currency that all energy-needing reactions in your body use, which is a lot of reactions. The concentration in your cell at any given point of ATP is anywhere between 1 to 10 millimolar, which is actually not incredibly high at any given point. And the total content in you at any given point is about 0.1 moles. I'm going to convert this. Okay, now I'm curious about this. What is the molar weight of ATP? 507 grams. So you have somewhere in the neighborhood of 50 grams in you at any given point. Wait, did I do that math already? Okay. But in a day, you use anywhere between 100 to 150 moles of ATP, which means that you use, if it wasn't being recycled, that's about 50 to 75 kilograms of ATP. But since we are in Canada, hold on, I'll convert that to pounds because I want this to make maximum impact. Convert 75 kilograms to pounds. 165 pounds.
Thanks, Google.
165 pounds of ATP a day. It's a good amount. Each molecule of ATP is recycled somewhere between 1,000 to 1,500 times per day. A lot. On average. Some are going to happen more than that in more metabolically active tissues, some less than that. But on average. All this is to say, ATP is really important. The other thing you could say from this is, if we just hook ourselves up to like a big vat of ATP, keep pumping it into you, and somehow get the old ATP out, you wouldn't have to eat.
How nice that would be?
Yeah, you use a little wheelbarrow of like 165 pounds of ATP behind you. It's kind of like
It turns like a little backpack.
165 pound little backpack?
I just like get a tank with a lot of crap in it.
What's that? It could be as small, but 165 pounds to 165 pounds. The math doesn't go anywhere. Yeah.
We still need fats and other.
Yeah, we still need other things. You just take your multivitamin at the beginning of the day, though. And like the fats, you can synthesize from other things. Yeah, so like you just take like your
More ATP.
make it off of ATP. And I'm just talking about, yeah, you need other things. And there's all these like cofactors that you need, and a lot of things you can't make, and there's like amino acids that you can't make. So yeah, like literally you can't do this. I don't want anyone to leave thinking you can literally do this. But that being said, maybe we'll do this. That sounds fun. Okay. Oh yeah, we should do that for lab. hook you all up to an ATP vat and give you all wheelbarrows to drag it around. Okay, so remember there is a quiz that is due by Wednesday at 10 a.m. I'll remind you on Monday. Also remember, if you didn't take the first one, I'm going to open it up very briefly again for a 20% discount. And